All right, we're recording, and now we're focused on Taylor-Maclaurin series, section 8.7. So you learned in section 8.6 a way to take a function and express it as a power series over an interval of convergence. And it was based on the fact that we could take 1 divided by the denominator 1 minus x and write that as a geometric power series with a radius of with a ratio, common ratio equal to x. Okay, and then from there we were able to do 1 over 1 minus an apple and come up with a geometric series where the common ratio was an apple. And so we could take functions using those formulas, write them as power series over certain intervals of and then find an interval of convergence for which the power series was equal to the function. But and that's great, but there are a lot of functions we want to find power series for where the technique of section 8.6 will not work. Okay, like for instance, I might want to find a power series for the cosine function or the sine function or the exponential function. Okay, those are functions that you didn't see in section 8.6. So we want a more general way to write a power series for a function, and that's where Taylor and Maclaurin series come in. And this is probably one of the most important sections in the entire textbook. So, all right, let's go down here. So we start off saying, okay, let's suppose that a function can be represented by a power series. The power series is highlighted in gray here. So the f of x equals some c sub 0 coefficient, well, it's a c sub 0 constant, plus coefficient c1 times x minus a plus c2 times x minus a squared, plus coefficient c3 times x minus a cubed, and so forth. And that the absolute value of x minus a less than the radius r, that's a fancy way of saying over some interval of convergence. So let's suppose that a function can be rewritten as a power series of this form. Well, for this power series to be useful, we need to figure out what the value of a is and what the values of those coefficients are. Okay, so we can uniquely determine the power series. Well, the value of a is normally given to you in a problem. Okay, and you'll see this in examples. The coefficients, well, okay, how would we find these coefficients? All right, well, they say, and let me just make a little adjustment here. Hold on. So let's try to determine the coefficients, what they must be in terms of the function. Okay, so what they do is they say, okay, well, let's substitute in, and I'll highlight this. Let's substitute in x equals a in that equation above. So in other words, we're going to evaluate the function at x equals a. If we do that, all the terms in the power series would drop out except would equal 0, because a if x minus a is in all those terms except the first one, and a minus a is equal to 0. So if we put x equals a into the power series, in other words, we're evaluating f of a, then all the terms drop out except that c sub 0. And so c sub 0 would equal, let me move it down here. Hold on. C sub 0 would equal f of a. So now we've determined a value for that first constant. And that's a general formula. C sub 0 equals f of a. Are there any questions so far? Okay, well then let us proceed on here. Let us proceed on. So next we want to determine the value of C sub 1, which is the coefficient of x minus a. Well, what we can do is we can differentiate the power series. Okay, so we can differentiate the power series. F prime of x would equal C1 plus 2C2 times x minus a plus 3C3 times x minus a squared, and so forth. Okay, this would be the, hold on, let me just, I want to see how much I can get. Yeah, I think I can fit them both here. Maybe. There we go. So you see that if we differentiate the function f of x at the top there, differentiating the function is the same then as differentiating its power series. The derivative of the power series is what you would see in Formula 2. Okay, are there any questions on that? Any questions on the derivative you see there, f prime of x in the second equation? All right, well, what we want to do is do the same thing we tried before. Let's figure out what would f prime of a equal. So if we let x equals a, if we substitute that in all the terms, all those terms are going to drop out except C1. So C1 equals f prime of a. How about that? Now we know what that first coefficient is. C1 is f prime of a. Okay. Well, now let's try to find C2, C sub 2. We're going to now differentiate again. We can differentiate the derivative function f prime of x and get then the second derivative that you see in equation 3. F double prime of x will equal then 2c2 plus 2 times 3 times c sub 3 times x minus a plus 3 times 4 times c sub 4 times x minus a squared, and so forth. Okay, I mean, we're differentiating a polynomial is easy, right? So now what we're going to do is we're going to put in x equals a on that second derivative. So f double prime of a would equal, well, what would it equal? Well, again, all the terms drop out, and you get f double prime of a equals 2 times c2. And that means c2 is f double prime of a. Okay, so hopefully we're going to start detecting a pattern here. Okay, on finding these coefficients. Hopefully we're going to detect a pattern. Well, let's do one more. Let's do one more. Let's differentiate that second derivative. If we differentiate the second derivative of f, we get the third derivative of f, which is in equation 4. You see how we're just iteratively differentiating here? And we'll let x equals a. And if we do that, then the third derivative of the function at x equals a is just 2 times 3 times c3. I mean, how beautiful is this? Okay, so all right, let me go to the whiteboard and let's write down so far what we know. Here, let's write down what we know. So hold on. Okay, so C sub 0 is f of a. C sub 1 was f prime of a. Okay, hold on here. All right, and then so we have two coefficients here, completely defined by formulas. We learned that the second derivative of a is equal to 2 times C2. Well, this means that then the second derivative of a divided by 2 is equal to C2. There's that second coefficient, or the third one, I should say. And then we learned that the third derivative of a was equal to 2 times 3 times C3. Okay, so then the third derivative of a over 2 times 3 equals C3. And notice that we could put like a 1 here and a 1 here, right, without loss of generality. What do you think C4 is going to be? Based on sort of the pattern you're seeing here. And incidentally, f prime of a, I can put 1 there. What do you think C4 is going to equal? Okay, hold on, Taj. That's right. The fourth derivative, evaluated at a, divided by 1 times 2 times 3 times 4. But you'll notice that's just 4 factorial, right? That's 4 factorial. Notice also here that C3 is the third derivative of the function evaluated at a over 3 factorial, right? And C2 is the second derivative of a over 2 factorial, because 1 times 2 is 2 factorial. Okay, so if I highlight them in black, we're hold on. Okay, and C1 is f prime of a over 1 factorial. 1 is equal to 1 factorial. And C sub 0, by the way, is f of a over 0 factorial. 0 factorial equals 1. So this means then that we can deduce that for this power series representation of the function, so long as the function is continuously differentiable, the coefficients can be found by taking the nth derivative of a, the nth coefficient can be found by taking the nth derivative of a and dividing it by n factorial. Pretty cool, huh? And this is a very general approach, very general. We just need the function to be differentiable, but it's very general. Are there any questions? All right, well, let me get back to the book then. Finish this idea up here. So, okay, so we've basically now, this is right. We know how to find the coefficients and of the power series, and so we have now this theorem that if the function has the power series representation below, then the coefficients are given by that formula. So we can substitute in the formula, the nth derivative of a divided by n factorial for all the coefficients in the power series. And if we do that, we come up with what we call the Taylor series. Okay, the Taylor series, named after Brooke Taylor, who lived from 1685 to 1731. Okay, so here we go. That's a Taylor series. It's a Taylor series of a function at A or centered at A. That's a Taylor series. So we're writing a function as its Taylor series. Of course, there's an interval of convergence, right? That we have to take into account. But there you go. Are there any questions on that? All right. Well. So we have to know. We have to be able to, of course, pick a value of a for our power series. And in the example, I'll show you basically. I mean, right now, you're going to be basically you'll be told what the values of a are. Now, I want to say one thing. If the value of a is 0, if it's understood to be 0, then that's a special case of the Taylor series, and we call that a Maclaurin series. For the special case that a equals 0, the Taylor series becomes a Maclaurin series. So that's just the Taylor series where the value of a equals 0. And many types of functions are expanded about 0. Are there any questions? Okay, let's do a few examples here. Let's do a few examples. Okay, let me give you a moment to copy this example down. So this is a function here. We have the cosine of 3x divided by 4. Okay, so this is a trigonometric function. And we want to be able to write that function as a Maclaurin series. So a Maclaurin series means A equals 0, right? We're expanding the series about A equals 0. So for the Maclaurin series, and let me bring up the Maclaurin series from the ebook here, one moment. Hold on here, let me find it. Okay, there's the Maclaurin series. What is necessary to find to create the Maclaurin series for this function? What do we have to find regarding the function to create its Maclaurin series? That's right. That's right, Tosh. We have to find derivatives of the function and then evaluate those derivatives at a equals 0. Okay, that's how we're going to get the terms of the series. The terms of the series depend on the derivatives. So, okay, well, that's fine. We can do that. So here's the function, cosine of 3x divided by 4. And let me go to the next page where I'm going to show you the, portion of the solution here. Okay, so what I choose to do is I choose to find the first 4 derivatives of the cosine of 3x over 4. Okay, I find so of course we're using the chain rule. Okay, I always have to adjust the font here. Okay, so I get the first derivative, second derivative, third derivative, and fourth derivative. And I'm going to let you copy here. And then I evaluate those derivatives at 0 because A equals 0. And I get these values. So I'm going to just let you copy. I don't think I need to describe the math here. You've seen this math, but I will say, you might be wondering, well, why, Dr. Duty, are you taking 4 derivatives? Why not just 2? Well, I have to take enough derivatives so I can detect what the pattern is for this series. I want to find the series. I need to find its formula. So I need to take enough terms. It's like a sequence, The sequence normally to determine the formula, you need to take enough terms to sort of figure out the pattern. Same kind of thing here. All right, let me let you copy down to here. All right, and please let me know if you have any questions. Okay, so now what I do is, all right, well, the Maclaurin series, I create the Maclaurin series right here. And I put in the details, um, you have the factorials in the denominator, and then you have the coefficients are the derivatives uh, at 0 of the function, except of course the first term is f of 0. So let me just see here. Maybe I'll make my font a little. F of 0 is 1. F prime of 0 is 0. F double prime of 0 is negative fourths, negative 9/4, and so forth. Okay, so you just construct the series. Now looking at these numerators here, what do you think the next term in the series would be? If I wanted to like put in the next term in the series, what power? Well, I mean the next of course. Well, what would the next non-zero term be in the series? What like x to what power would go with the next non-zero term in the series? X to what power? So x to the fourth is, we know that term. What would the next non-zero? That's okay. No problem. What would the next non-zero term be? The next non-zero term. So you notice we have, that's right, Javier, x to the sixth power. So if we were to put in, let me just see here. If we were to put in some term, okay, this is the next non-zero term. What do you think is going to go here in front of x to the sixth power? Well, and would the term be positive or negative based on the pattern that you're seeing here? Would the term with x to the sixth power be positive or negative? What do you think? It would be negative. You can see you have a positive, a negative, positive. That's right, Mario. And so this next term has to be negative. Okay, it has to be negative. That's fine. And Mario, you got it right. Good. Good. The next term here would be 729 over 4. Okay, because if you look, like 1, 9, 81, 1, 9, 81, 1, 9, 81. You know, like 9 is 9 to the first, 1 is 9 to the 0, 81 is 9 squared. So 9 cubed would be 729. Okay, so I just want to kind of, you know, put in that other term. Now what we'll do, this is on the next page as well. Let me go to the next page. Let's continue this. So we're continuing the problem. We're continuing here. So now I write the power series out so that I have 4 non-zero terms. I mean, I've written down 7 terms, but 3 of those terms are 0. So that leaves me, I mean, I've written down 7 terms of the Maclaurin series, but 3 of those terms are 0. So that gives me 4 non-zero terms. That should be enough to detect to get the general formula. Now, this term here, negative 9/4 over 2 factorial times x squared. The 2 factorial, you can put that over 1. And that'll give you negative 9/4 times 1 over 2 factorial times x squared, which is negative 9x squared over 4 times 2 factorial. And that's what we have here. So I'm trying to show you how I get from this term to writing it like that. Just trying to show a detail. I'm going to turn my email off. I don't want any distractions here. And then the rest of the terms follow suit, right? You can similarly rewrite those. Turn off that email here. I don't want any distractions. This is your time, right? So now that we get the series, the power series in this form, we can come up with a formula. So the 1/4, incidentally, you can think of 1/4 as 1/4 times 0, well, times 0 factorial times x to the 0th power. Which is like 9 to the 0th power. Then you have 9 to the 1st power. 81 is, well, actually, hold that thought. Yeah, 81 is 9 squared. 729 is 9 cubed. So in general, I want to be a little bit careful about this. In general, in those numerators, you're seeing 9 to the nth power. But 9 to the nth power can be thought of as 3 squared to the nth power, which is 3 to the 2nth power. And that's how we get this. So what's going to happen is in your homework for section 8.7, you're going to be, I mean, I'm like in section 8.6, when you had to come up with a power series, you're given a multiple choice problem, right? Find the power series for this function, and then you're given a list of choices, and you have to select the right choice. Well, you know, you might say the formula. I mean, you might say, oh, the formula is -1 for the formula for the series is -1 to the nth power, and then I have 9 to the nth power. But maybe in WebAssign they won't have 9 to the nth power. Instead, they might have 3 to the 2nth power. So you have to be able to, recognize that. Okay. All the terms too in the series are even. So x to the 2nth power, okay, will give you just even powers of x. The factorials are even also. 0 factorial, 2 factorial, 4 factorial, 6 factorial, they're all even factorials. Well, 2n factorial will give you even factorials. So this here is the answer. This is the Maclaurin series for the cosine of 3x over 4. And of course, naturally, we want to know, well, for what values of x is this true? For what values of x is this true? To do that, you have to find the interval of convergence using the ratio test, which you've done quite a bit of. Are there any questions at all? All right, well, let's go ahead and find the interval of convergence. If we're good, I'll go ahead and move to the next page. So naturally, by the way, your nth term is here for the power series. And so we just proceed forward. Whoops, hold on. Make that a little bit bigger. Right, the nth term. Okay, let's go forward. So here we're doing the ratio test. Very important, right? Very, very important. So there's the nth term. And there's the n plus first term. So as you know, to get the n plus first term, anywhere you see an n, you replace the n with n plus 1. Which we did here. And then this is just really, I'm just going to let you copy. I'll make a few comments, but just go ahead and copy it down. So of course we want to simplify the ratio, and naturally I group together like terms. On this step here, hold on. On this step here, I multiply by the reciprocal of the bottom fraction, and then this step here I group together like terms. And then the 2n plus 2 factorial is the same as 2n plus 2 times 2n plus 1 times 2n factorial, because 2n factorial is just 2n times 2n minus 1 times 3 times 2 times 1. Okay, and what happens is the factorial terms, the 2n factorial simplifies out with the 2n factorial, and the 4's also simplify out. Hold on here. The 4's simplify out, and you reduce it and you get here. And this we're going to do the absolute value of this expression. And so the negative goes away, and the 3 squared is positive, the 1 over 2n plus 2 times 2n plus 1 is positive, and x squared is always positive. So we can drop the absolute value signs. This is our common ratio, our limiting common ratio. Well, this is our common ratio. And as n gets large, the denominator goes to infinity. So whatever x value is on the top, whatever value it is, x is like it's a value. There are different values of x, but it's a value. And when we let n go to infinity, no matter what that value of x is, the denominator is going to go to infinity and produce, in the limit, you'll have a 0. 0 is less than 1 for all x. So that means your interval of convergence would be from negative infinity to infinity. Are there any questions? All right. Well, then if I go to the next page, if everybody's good, I'll move to the next page then. Okay. So we have our interval of convergence. It's all real numbers. And so we can say then that the cosine of 3x, hold on. We can say that the cosine of 3x divided by 4 is equal to its Maclaurin series. Okay, hold on. It equals its Maclaurin series. And that's true over, well, I can't fit. It's true over the interval from negative infinity to infinity. Absolutely beautiful. Absolutely beautiful. So Maclaurin series have been established for a number of different functions. And the book has a table 1 in section 8.7, which I'll show here before we go on to break. The book has a lot of good examples. But this is important Maclaurin series in their radii of convergence. Now, of course, the radius of convergence means they took the interval of convergence and took the distance and found half of the distance, half of the length. But at any rate, you can see there you have power series for all these different very important functions, like the exponential function, the sine function, the cosine function, the arctangent function. Well, the arctangent function, you actually found that there was power series for that back in section 8.6. So it should be the same, right? But this is a table of important Maclaurin series, and it's a table that you can reference when for some of the homework problems in section 8.7. So, all right, I want to stop there, and let me go ahead and stop the recording. Excellent.